Assalamu alaikum wa rahmatullah. Hello everyone, this is Islam Rida and another video of the pump series. Today we are going to recall the basics of hydraulics. We will also discuss some misconceptions regarding pumps. Let's start with fluid properties. The fluid properties of concern in hydraulics are density, viscosity, and vapor pressure. The density of a liquid is how many kilograms is there in a 1 meter cube tank of this liquid. We will denote density by rho and give it the units kilogram per meter cube. Two properties are derived from density. The specific weight gamma is how heavy is 1 meter cube of the liquid. It is simply the density multiplied by gravitational acceleration. Finally, the specific gravity is the density of the liquid relative to the density of water. It is unitless and hence it attains the same value in American units and SI units. It is always useful to keep the properties of the most common liquid, namely water. The density is 1000 kilograms per meter cube and the specific weight is 9800 newtons per meter cube. The second property is the viscosity. The viscosity indicates the resistance of a liquid to flow in a pipe, or the resistance of water to the swim of a fish, i.e., the viscosity is a measure of the fluidity. The shown are 5 different categories of oil of different viscosities. They display different degrees of fluidity. The viscosity as a property is expressed mathematically as dynamic viscosity or simply viscosity and kinematic viscosity, which is the dynamic viscosity divided by the density. Each has a few units. The viscosity of water is 1 centipoise and kinematic viscosity is 1 centistokes, which are equivalent in SI units to 10 to the power negative 3 and 10 to the power negative 6. The third property is the liquid vapor pressure. Please watch this video.
The next little demonstration we call boiling in a syringe. It's another one of those that's put away in a drawer and you can quickly grab and use when you're talking about boiling and boiling points. And most of us know that under normal atmospheric conditions, the boiling point of water is 100 degrees Celsius at 1 atmosphere. And a lot of people think if it's boiling, it's 100 degrees. Well, over here I have some water that's been heated a little bit. And actually there's a nice thermometer here, so I'm going to look at the thermometer and see what it's telling me right now. It's cooled off some from where it was. But right now, it's reading about 82 degrees Celsius. So we're going to take a syringe, and we have a little valve on the bottom of this, and we're going to pull in some liquid. Whoop, I want the 82 degree liquid. There we go. Pull in some liquid. Now, one of the vital things is to try to get rid of the air bubble at the top. So I'm going to try and just get rid of a little bit of air. There, I'm going to close it. And now, we're going to reduce the pressure on the water. Remember, it's 82 degrees. So here we go. And it's boiling very, very well. Notice something else, though. It boiled very rapidly to start with. And now it's slowing down quite a bit. Now that's a little more chemistry. Because in order to make something boil, we normally end up having to heat it. Boiling is an endothermic reaction. You have to put heat into water to make it boil. So now here we weren't putting any heat into the water, so the heat must have been coming from the water itself. So the water is cooling down. And the more it cools, the harder it is to make it boil. Now let's try this at a little bit colder temperatures. I brought another jar in. This was simply taken out of the hot water tap a little while ago. And it's reading 47 degrees Celsius. So that's quite a bit colder. And so we're going to pour a little bit of water in there. And again, get rid of the little excess, like that. Now, from the previous experiment, we should expect something a little different. If I can make it boil, it should boil, but what should happen very quickly? It should slow down and it should stop relatively quickly. So here we go. We're ready? We're going to try it again. There it is. It's boiling, but now it's starting to slow down already. It was boiling at 48 degrees Celsius. Now, I wonder what would happen if we went colder yet. Now, this was not that easy at 48, so it's going to be harder and harder. It is possible to actually put water in a vacuum pump, and it has a pretty good what we call vapor pressure, so it's always evaporating some, so it's hard to get the pressure really low on it. But physics teachers sometimes take water in a vacuum pump, a thin layer, and they take a little beaker with sulfuric acid in it that pulls moisture out of the air rapidly, and they end up creating a vacuum, and the water actually freezes. You can freeze water by reducing the pressure on it. That's really kind of neat. Now, I don't recommend you doing that because the sulfuric acid in the vacuum pump tends to end up getting into the line and the oil of the vacuum pump, and that means your vacuum pump does not last very long, and high school principals do not like to pay for new vacuum pumps. Okay.
So what was that? Assume water at atmospheric pressure. At what temperature does it boil? Yes, 100 degrees Celsius. This temperature is needed to break the connections between water molecules. Now assume water under high pressure, say 2 bars. Here the pressure causes the molecules to be closer and their connections stronger. Water needs more energy to get liberated, say 120 degrees. This is the principle of all boilers and pressure vessels. You need high temperature to increase energy or cook in a short period, but water must not boil. Now let's consider the reverse case. What happens to water under a low pressure? The molecular connections are weaker and water can boil at 80 degrees only. The lower the pressure, the lower the boiling temperature. At a certain very low pressure, the molecules are very weak and water boils at the operating temperature. This pressure is called vapor pressure, which is the pressure at which a liquid boils during operation. If the pressure in a hydraulic system is higher than the vapor pressure, this guarantees pumping a liquid. Otherwise, the vapor bubbles form through the pipe. Pressure is our main parameter. Let's settle some concepts regarding it. A very well-known term in hydraulics is the pressure head. Assume a pipe you want to measure the pressure inside. Drill a hole and connect to a vertical piezometer tube which will read a height h. The pressure is equal to rho gh. This equation can be expressed in a different way as h is equal to P over rho g or P over specific weight gamma. H defines the pressure head. So the head is another unit of pressure, like the bar and psi. For example, what pressure head of water is equivalent to 1 bar? The bar is 10 to the power 5 Pascal and the head reads 10 meter water. Yes, 1 bar pressure is equivalent to 10 meters of water head. Therefore, in a typical domestic water network where the pressure is 1 bar, the water column can rise to the 3rd or 4th floors with no pumps needed. Two important basics of pressure should be kept in mind. First, for any connecting series of non-flowing water bodies, the pressure equates over any horizontal plane. The pressure does not change with the shape or size of the vessel or connecting pipe. The second basic is that in a stationary non-flowing fluid, like water in this column, the pressure increases as we go deeper. As you can see, the water jet gets stronger with depth. The pressure difference between any 2 points in a vertical plane equals delta P rho g delta H. Let's add some motion to our fluid. Liquid flow in pipes is governed by 2 equations. First, the continuity equation, which states that the flow rate is a constant along the pipe and equal to the area at any section times the velocity at this section. As the pipe diameter increases, the velocity decreases, but the flow rate stays the same. The second governing equation is the Bernoulli equation, which is a hydraulic version of the energy conservation principle. A flowing liquid has a potential energy, a kinetic energy, and a pressure energy. The sum of the three energies is constant along the pipe, excepting the amount of energy or pressure head lost in friction with pipe wall and the hydraulic components. The amount of head lost in friction with pipe wall is equal to F friction factor times L pipe length divided by D pipe diameter multiplied by flow velocity squared over 2g, while the amount of head lost in friction in a hydraulic component is equal to K, the loss coefficient of the component, multiplied by the kinetic energy of the flow. Now to the main dish, 8 myths about pumps. Myth number 1. Consider a variable diameter pipe like the Venturi tube shown here. The pressure, as we know, is equal to the force divided by the pipe area. This means the pressure at the middle section will be maximum since the area is minimum. Truth. Who said the force does not change? We have to abide by the flow governing equations. According to the continuity equation, as the area decreases, the flow velocity increases. And according to Bernoulli principle, for the liquid to speed up, it must spend some of its pressure energy. Hence, the pressure is minimum at the middle throat section. Watch these videos.
What you'll see is when we turn on the air, this column of water in the middle will rise because the pressure here is lower and essentially acts as a suction for the water. So this one will rise higher than either of the other two.
The Venturi apparatus is comprised of a Venturi section connected to 11 piezometers. From left to right, the piezometers are labeled A to L, skipping the letter I. Next to each piezometer is a graduated scale. The valve on the right-hand side is used to regulate flow through the Venturi apparatus. Ensure that the power cord is plugged into the wall. Make sure the valve of the apparatus is turned off by turning the red valve clockwise. Start the pump. Remove any air bubbles from the manometers by tapping gently on the manometer tubes. Make sure that all the manometer readings are high and approximately equal. If not, seek help from the lab technician. Check that the Venturi device is operational by increasing the flow and observe the pressure drop in the manometers. The pressure drop should look like the following.
Myth number 2. I don't have enough water at my 5th floor apartment. I'm gonna use a smaller pipe size. Truth. Assuming this will squeeze water out of your pipe, it will restrict the input water as well. It doesn't work like that. Again, obey the flow equations. If you replace with a smaller diameter pipe, the friction loss in the new narrow pipe will be larger. The correct procedure is to increase pipe diameter or install another pipe in parallel to the existing one. This allows the liquid to flow smoothly like a car on a highway.
So, part 2 here is water flow as it varies with pipe size. All right, so we're back in the laboratory again, but a little bit different setup here. I got a 5-gallon bucket here. I'm going to do a 30-second flow rate with the same setup, the same setting on our sink, so wide open. And I've got 2 different specimens here. I got a 3/4 inch pipe flowing through. I've got a 1 inch pipe or a 1/4 inch pipe flowing through. Going to be hooked up the same way. We're going to see what the difference is in filling up the bucket. So here we go. Okay, 30 seconds later. Yep, there's a difference. So I know y'all can't see this, so I spun this around so you can see it. So first test with this guy, filled it up to here in 30 seconds. Second test, which we just got done doing, filled it up to here.
Myth number 3. How does a valve control the flow pressure and throughput? Maybe because it has a smaller area than the pipe. Smaller area means a lower velocity and maybe a smaller flow rate. Truth, if this was the case, then why the pressure stays small downstream the valve in the large pipe? Actually, the valve forces the liquid in a non-streamlined path, which leaves stationary liquid pockets. These water pockets are sheared by the flow and form small eddies. The eddies consumes the flow energy and cause a lasting pressure loss. Myth number 4. How much pressure does this pump generate? Truth, a liquid can't be pressurized unless it is compressed from two sides, the pump side and the system side. Let's see a common example. Assume a pump discharging to the atmosphere. What pressure do you expect on the delivery side? Yes, 0 atmospheric pressure. Now, let's assume the same pump is fixed in a hydraulic system which raises 1 ton load. The pump has to overcome the load to push the liquid, thus the pressure rises to a high value equivalent to the system load. In conclusion, a pump can generate any pressure depending on the system where it is installed. Myth number 5. A large pump produces higher pressure. Truth, as we said, the pressure is not a pump property. A large pump simply delivers more throughput. Note that more flow means more friction, and this can indirectly lead to pressure increase. Myth number 6. The pump increases the flow rate. This means a pump sucking 5 liters per minute can deliver 10. This is totally wrong. The pump transfers liquid, not creates it. This violates the conservation of mass principle. The delivery must be the same, 5 liters per minute. So what's the point of the pump? A good question. The pump helps the liquid to overcome the system resistance. Unless the pump, the flow rate will be 1 liter per minute. A similar situation arises with the valve. If the flow upstream water tap is 0.5 liter per minute, then the flow downstream will be also 0.5 liter per minute. The valve adds to system resistance such that if the valve is not there, the flow will be 1 liter per minute. This is a sample garden swimming pool. The pump is used to filter and circulate water. As I said, if the suction flow rate is 5 liters per second, the discharge will be 5 liters per second as well. If the suction and discharge flow rates of the pump were not equal, the water level in the tank will increase until spilling out of the pool. This never happens for sure. Imagine replacing this pump with a larger pump. The flow rate will increase on both sides of the pump, i.e., the circulation and filtration rate will increase. Myth number 7. The pump performs better or delivers more water if placed near the water source. Truth, basically, there is no scientific evidence that the place of the locomotive in the train matters. So why plumbers do not like placing the pump at your 4th floor apartment? Then storing the pump near the water source at ground floor guarantees handling high pressure with minimum chance of vapor formation. Myth number 8. It is safe to run a centrifugal pump with its delivery valve shut. Truth, although shutting off the delivery valve does not cause overpressure in a dynamic heat pump, but it still can cause overheating, since the pump relies on water flow for cooling. So running the centrifugal pump with a closed valve for a long period can harm the pump, especially in poorly ventilated areas. This was a quick revision of the basics of hydraulics and some of the common misconceptions regarding pumps. For more information or to download the PPT material, refer to my website in the description box. In the next video, we will talk about the centrifugal pump. Thanks for watching and see you inshallah.